Anyway, thank you very much, Barbara, for inviting me. It's my first time traveling in 2 years, it feels like, so it's kind of a treat. So I'd like to give kind of a review of some work we've been doing over a number of years. And it's not so much to say, oh, this is the way the Earth is, or these are the correct results. It's much more, what I wanted to do is give an approach to you to maybe think about in your own research and how to approach the problems of geodynamics, the dynamics of the mantle, and the composition of the mantle. And this is work with a few students of mine, and especially Alessandro Forte at University of Florida has provided all the geodynamic part of the work. So to begin with, whoops, there we go. I'd like to talk a little bit about the tomography I do, just very, very briefly, but my approach has been to look at seismograms. This is an example of a SH wave seismogram. We're going to be looking at shear wave tomography. I used synthetics over the years to try to predict, these different waves, and this is an example of a synthetic here. And you can see the wave shapes are matched, and there's a whole bunch of different waves. The ray paths of those waves are shown below here. And because of all these different waves that you see in SH, you really have a good sampling of the mantle going down. The big arrival in the back here is the love wave, and we actually use that as well. It's not labeled here, and that would be sampling even more shallow than those ray paths going along the surface. So what I did over a long number of years is look at a lot of seismograms, try to extract from them with this kind of waveform modeling travel time deviations from some starting model for those paths. We still use a very old-fashioned way of how we invert those travel time anomalies to get a structure. Basically, we still use a block system to divide up the mantle, assume that anomalies in each block are uniform, and then for the different paths going through the block, you can relate the travel time anomaly to the velocity anomalies in the blocks. And we just use, still use ray theory, so path length as the kernel if you want. So you end up with a series of linear equations. The L here is all those ray paths, the unknowns here, the model, and the residuals there. I'll mention also that in almost everybody's tomography, you apply some kind of smoothing or regularization. So that's what's meant here. D times these model parameters equal to 0. In other words, adjacent anomalies have the same value. You can use that or different forms of that kind of regularization. So a lot of different approaches to doing seismic tomography. People use different kinds of waves, P&S waves, surface waves, normal modes, etc. Over the last 10, 15 years, a lot of different approaches. You've probably heard terms like finding frequency kernels, full waveform inversion, etc. And also people parameterize their models differently. We were using blocks, you can use nodes or different things like that. Regularization is different as well. What I wanted to mention is all these different approaches end up with linear equations like I showed you in the previous slide. It's just that the kernels, instead of the L, the path lengths in blocks, some of those kernels are much more sophisticated. That's the finite frequency kernels, or even in what we call full waveform inversion currently. So they're all pretty similar in the end in terms of what you actually do for the inversion. So I like these slides. These are some different models here. You can see which models they are up at the top, and I compare them. I'm just going to show you 2 depths because of time constraints. But at shallow depths, 60 kilometers, you look at these different models. Basically, you see plate tectonics. You can see the ridges, etc. There are differences in detail among models, but to first order, they look very similar. If you look at this model here, this is Jeroen Ritsema's, you see a lower amplitude than what you see in the upper models, and that's probably just purely his regularization. He uses a little more regularization than other people. The other thing I should mention about these slides, and the next one I'll show you, is we took all those models, expanded them up to degree and order 40 spherical harmonics, and they're in the same amplitude scale, so everything is the same. Sometimes if you look at the models, different ways of presenting them, they look more different than they actually are. So I just have one other depth I'll show you that for. So somewhere in the middle of the mantle, 1,100 kilometers depth, you look at the 4 different models and you can say, gee, they're very different, or they look similar depending on your personality, probably more than anything. But what I find is kind of amazing. In the next slide, what I did is put boxes over certain features, and there are identical boxes throughout the models. And what impresses me is that in detail within those boxes, you see differences, but every model has faster than average seismic velocity in the boxes. And some of them are kind of interesting, like here, south of the Aleutians. Every model has a fast anomaly there. It's south of the Aleutians, I think in terms of plate tectonic reconstructions, understanding how slabs sink into the mantle, it's an interesting feature. Another one I find interesting is going through North Africa. Again, every model has something there, and here's another feature. Southward all the way down to Madagascar, and again, well, not so much this model, but these three models all have fast anomalies there. So to me, looking at that, I think, gee, in detail, any one of these blocks, if you want to take it, so I don't know, this one, for example, the models look a little bit different, but they're all faster than average within that particular block. So there's some progress being made there. There's some real features in the Earth coming from all the different tomography, but in detail, they're a little bit different. The slow anomalies for the same figure, this is the same idea, they're a little bit different, but the slow anomalies at this depth in the Earth are a little more ephemeral. They're smaller scale, but still, especially here across the Pacific Ocean in an east-west fashion, all the anomalies look similar. Same thing down here, over here, over here. Again, in detail, the features inside those blocks look different for different models. However, they're all slower than average from the different models. So I think that's, I have some other depths that I could show you after if you wanted, but I think that's pretty promising. Here's the base of the mantle, and of course for anybody who doesn't know, we have these large, low shear velocity provinces, 2 of them that all the models find and have found for a number of years. Again, in detail, they look different. For example, Barber's model over here, more short wavelength features than ours, smoother model. But the geometry of these large, low shear velocity provinces looks similar among the models. So, seismic tomography is kind of fun and interesting, but on its own, it's not really important, right? Everybody wants to know the dynamics of the mantle, the composition of the mantle, how it evolves, and just using the tomography alone, I think is difficult to do that. And in fact, there's still a lot of argument. So if we could get density as well as the seismic velocities, that would go a long ways, or would help in terms of understanding chemistry and the dynamics of the mantle. However, that's kind of challenging, especially from a seismology point of view. So there have been some studies specifically looking at density. Way back, Ishii and Tromp found that African large low shear velocity province, slow anomalies, actually has higher density than average. They use free oscillations. But a recent paper by Kohlmeier in 2017, using free oscillations as well, report that it's actually buoyant, the African LLSVP. And then I put in Harriet Lau's recent paper using tidal tomography, saying, oh, they're denser. And Barbara actually had a paper back in 2002 saying using these free oscillations alone, it's a little bit different to get at density. So what we have, the approach we've used is to use geodynamic constraints to get at the density in the mantle. And the geodynamic constraints we use are the following. We have gravity anomalies that's related to mantle density anomalies. We have dynamic topography, which for us is the topography of the Earth when you strip out the effect of crustal thickness. So any kind of mantle density anomalies causing topography variations we call dynamic topography. And then we have the plate motions, and the way it's parameterized here is given the plate boundaries, what is the divergence and convergence at the plate boundaries? So that's shown here in a color map as well. And these are all expanded up to spherical harmonic degree 32. So those are the dynamic observations, geodynamic observations we use. We use one other one I should mention here. It's not written. It's the excess ellipticity at the core mantle boundary. That's essentially just one spherical harmonic component. So going way back to Brad Hager, you can relate an observation, say, of gravity of one of those geodynamic parameters to density anomalies in the Earth using a linear relationship. And the linear relationship G here is the kernels. This is shown over here for gravity sensitivity. It depends on the spherical harmonic of the field that you're looking at, what the depth variation of the sensitivity is. You should look at these curves. I guess you don't have time to look at them in detail, but essentially they're showing the sensitivity of a point density anomaly at a particular depth for that particular observation, either the harmonic degree for gravity in this case, same thing for topography, etc. Now these things depend on the viscosity as a function of depth in the Earth, and they are approximate in the sense that they assume a 1D viscosity model, so viscosity only varying with depth. So these particular kernels, we'll call them, are for this viscosity model over here. So there are many different viscosity models, and in this work, this comes from a paper by my student Chang Lu that came out last year, we looked at a number of different viscosity models going forward in this talk. So this is a picture of the 5 different viscosity models we used, and you can see here this is a logarithmic scale, so the different models that have been published for viscosity do vary by orders of magnitude in some cases. So we used all these different viscosity models to go forward in this particular analysis. Over here, this is a busy figure. You don't have to look in detail, but the different colors here, again, these are for kernels, I think degree 2 only. And the different colors here correspond to a different viscosity model. So you can see how the kernels vary with viscosity model. But we'll use all of them going forward, so I'm not choosing a particular one. So having those kernels for relating density anomalies in the mantle to these geodynamic observations that we have, we can take the tomography model and scale it. A lot of people do this, assume that, oh, a slow seismic anomaly is a low density, high velocity, high density, etc. We can use some kind of linear scaling, scale the seismic model, and predict those geodynamic observations. And again, don't look in too much detail at these things, but for gravity, the plate motions, dynamic topography, and the core mantle boundary, we do an awful job of fitting that data, just doing the simple scaling. And this is much worse maybe than some of you are used to, but probably some of you are used to looking at just the longer wavelength features like the geoid, for example. So we're going all the way up to degree and order 32, and this is the formula we use for the variance reduction. That's what you're seeing here, these numbers, just the difference in the harmonic components for those different fields, all the way up to degree and order 32. So we do a bad job, at least from the way we're doing this, in predicting that. So the approach we've used is, well, let's jointly invert the geodynamic observations as well as the seismic observations. And when you say jointly invert, well, if you connect the two, density to seismic velocity, then you can do the joint inversion. So if we use some scaling factor, density to seismic velocity, then we can set up in the same linear fashion for the geodynamic observations and the linear kernels here, times the same shear velocity anomalies here, model equal to the observations of the harmonic components of those geodynamic data. The omega here is the weighting. So the logic here is there's a pretty big null space in seismic tomography. So can we adjust the seismic model, still fit the seismic data, and do a better job of fitting the geodynamic data? And we still have the smoothing matrix over here. And one added complication we found pretty early on, that you don't do a good job at fitting these geodynamic data unless you correct for the craton. So again, we're assuming a connection between seismic velocity and density, some linear factor, constant factor in the mantle. But in cratons, we have good evidence that it's chemically distinct, intrinsically more buoyant. So we actually use a different scaling factor in cratonic mantle down to about 200 kilometers depth. And then you can run your inversion here. And our approach that we took is to change the weighting of the geodynamic data and see how you fit the data better. And we decided to try to keep the seismic fit. So down here is the variance reduction for the seismic data. The beginning model was here. Try to keep the seismic fit about the same. before the geodynamic data really starts to disagree with it. So the red stars here show you the weight that we chose for different viscosity models. The different colors here are for using the different viscosity models in these inversions. So doing that, we come up with much better fits to the data. So here's gravity. Thermal joint is what I meant by that inversion here, 40% variance reduction across the board here. This model is a bit of an outlier. We can talk about that after if you want in terms of a viscosity model. Plate motions are pretty well fit. Dynamic topography, about 50% variance reduction. So we do much better in fitting this larger data set, keeping the seismic fit the same. And I should have mentioned this. We call this thermal inversion because the assumption here with this kind of linear scaling between seismic velocity and density is, oh, the variations are due to thermal variations. And we use some mineral physics to constrain that scaling factor that we used in these inversions. So it's kind of a hypothesis test if you want. Maybe Occam's razor is a good analogy for a simple model for trying to interpret the mantle. So in our joint inversions, we do okay, but there's still a lot of misfit between the geodynamic data and the seismic data, assuming that thermal type inversion. So how much do the models change doing these joint inversions? So here on the left are the pure seismic inversions that we had before at 2 different depths. And here's the results from the joint inversions. And at least visually, the changes in the model are not that strong, if you want. One of the things I noticed is, gee, at 2,000 kilometers depth, the pure seismic had slower velocities than the joint inversion. And actually, we can talk about that a little bit later, too, if you want. So the changes in the model are not huge. So we still had significant misfit of the geodynamic data. And you can always just find a density model to fit the geodynamic data, but we approached it through an inversion here where we fixed that seismic model, we fixed the densities in it, and then we inverted for 3D scaling factor just for the densities to better fit the seismic model. So what we're looking at is, okay, we're changing that scaling factor between density and seismic velocity to better fit the geodynamic data. And we call that the chemical density anomalies. It's not necessarily a difference in chemistry. It could be a difference in the linear relation between seismic velocity and temperature. But in any case, that's what we do. We find a new or an additional density anomaly to better fit the geodynamic data. The total density field is that 3D scaling factor times our seismic model. The thermal one was the original, and what we call chemical density anomaly, just for a short name for it, is the difference between those two. If we do that, we can get quite good fits to the geodynamic data, same fits to the seismic data. So gravity here, we're up at 90%, different viscosity models, slightly lower for these models. These viscosity models were derived doing this process, so it's a little unfair comparison there. Since they were tuned to fit this kind of data, whereas the other models were not, but still quite good fits to the gravity data. Plate divergence, very well fit. Dynamic topography, a little bit less fit, but 80% variance reduction in this case. So in this process, we have these chemical anomalies, we have thermal anomalies, and I'll show you a few maps of those. Over here, the thermal anomalies, and over here, what we call chemical anomalies. So the red color here says you have some intrinsically buoyant material chemistry. It's exactly what you would expect within the cratons. So that's lower density than you expect from just the thermal velocities. And then over here is the total density field. So this is in the lithosphere depths, 100 to 175, or cratonic lithosphere anyway, and you see the strong signal of the cratons that's necessary to fit the data. As you go deeper, I'm just, again, for time, just show a couple of depths here, but down in the middle of the mantle here, this was our thermal density and the total density here. Notice the scale change. Thermal density, the scale is 0.4, total chemical 0.2. There's very little chemical, and the chemical anomalies that show up are kind of short wavelength. I'm not sure how significant they are, but much less. So there's little chemical heterogeneity with our definition of that needed in the middle of the lower mantle. As you go down to the bottom of the mantle, however, the slide is at the base, the D double prime region. Here is the thermal. You see the LLSVPs, of course, very slow velocity, very buoyant. But for these four viscosity models, we require some pretty strong chemical anomalies, and they're blue, which means extra density, so some intrinsically higher density material in these two spots, and very little elsewhere. So bottom of the mantle, top of the mantle is where our inversions really seem to require, how should I say, chemical heterogeneity. So looking a little more detail at the bottom of the mantle, the chemical anomalies somehow in the LLSVPs do not encompass the entire LLSVPs. They're more in the center with a lot of buoyant material around the LLSVPs. So I should say what you're seeing in this picture is the average total density. And by average, we averaged the four different viscosity models that looked fairly similar to come up with this picture of density down at the base of the mantle. The stars here are hotspot locations, and they do seem to locate above the buoyant parts of the LLSVP deeper down. And these are cross sections of the density field through the Pacific LLSVP along that line, the Africa one here along this line. You can see this chemically distinct feature within the LLSVPs, and these inversions anyway, pretty much relegated to the bottom of the mantle and not even the entire LLSVPs, but within the center of them. So if you have the density field using this theory, you can come up with the flow in the mantle. And these pictures here show the mantle flow calculated for our total density anomalies. The arrows show you the horizontal direction of flow, and the colors indicate the vertical direction of flow. So this is at 200 kilometers depth. I don't quite understand this, but when we use these two viscosity models, the magnitude of the flow seems to be larger than when we use these two viscosity models. And anyway, you can see kind of the picture, upwelling under the ridges and downwelling under the subduction zones. Not a big surprise there. But it is kind of interesting when you plot hotspot locations. So the green stars are hotspots. For many of them, for example, over here in Africa, I don't know, over here, Hawaii, we do seem to have upwelling. We haven't done a good correlation of there. Another one over here, Cape Verde. We do seem to have upwelling very localized underneath the hotspots through this inversion that we've done. And this is for one viscosity model, V1. I decided not to show the figures, but going back to these different models, we find pretty good correlation of the flow. Not exactly the same, but pretty good correlation of the flow for these four viscosity models, not so much for this viscosity model over here. So if you go deeper into the Earth, this is 600 kilometers. Again, this just shows you the flow here. Some of the differences in flow, for example, over here, what's that hotspot? I forget the name. Anyway, there's a hotspot over here. You can see this lateral flow, 600 kilometers depth, is different than the direction in these two viscosity models. So these two are more similar than these two in terms of the flow. But again, the overall pattern is quite similar among the top four viscosity models. Again, less so for this one down here, but this one had no lithosphere or asthenosphere in the viscosity model. One thing I will point out is major upwelling under the East Pacific Rise in all four of these different models. If we go deeper still, down to the bottom or deep mantle here, it's kind of interesting. I think the color pattern here in terms of vertical flow among those four viscosity models is really quite similar. I see 6 major upwellings in the planet, especially beneath the East Pacific Rise, kind of an interesting one. Over here, the Caroline hotspot, Southern Africa, and over here in the Indian Ocean. and over here in Cape Verde. And I think in some of these models, there's some indication of upwelling under Iceland, though maybe not as strong. So all 4 of the different viscosity models from the approach we've used have these major upwellings in the deep mantle, maybe 6 of them. So that's, am I going, okay. I'll finish in a couple of minutes. That's a model of the flow. We have some indication of chemical heterogeneity in the mantle. That's kind of what we're after. This, I think, is quite interesting, and this was published by Dave Rowley in 2016. As I mentioned to you, we have major upwelling coming up under the East Pacific Rise over here. So this is the cross-sections along this line through these different viscosity models, inversions that we have. And the black line there indicates roughly where the East Pacific Rise is. And all of these models have major upwelling coming up in that location. And one of the things, maybe a little takeaway point is, you'll see here the colors here are the density that we found. But you have regions, say, where there's no density anomaly, but they're still upwelling. You have regions where, oh, it is lower density, but there isn't any upwelling. So because of the high viscosity in the mantle, it's a little difficult to just look at a tomography picture and say, oh, that's going up because it's slow, and that's going down because it's fast. So that's one little takeaway here. But the bigger takeaway, I think, is the fact that we get this upwelling in the under the East Pacific Rise. Over here, in this figure here, is taken from a paper by Conrad and Ben back in 2010, where they just scaled the tomography model and got the flow of the mantle from that scaled model. And they do not have upwelling under the East Pacific Rise. They have it coming up more over here, where we have actually dense mantle at the bottom of the LLSVP, or in the LLSVP, and they have the flow coming that way. And look, especially in the asthenosphere here, they end up with reversed flow like that, whereas our situation is quite a bit different in terms of asthenospheric flow. It's maybe a little bit hard to see it there, and really the dynamics of what's happening under the East Pacific Rise. So I just show that to show, gee, the approach we used is coming up with a different dynamic field than you would get just from pure scaling. And I got just 2 slides left, and then I'll finish. Dave Rowley in his paper noticed that the East Pacific Rise is quite interesting in the south. It has asymmetric spreading. So the dashed line here is the 35 million year paleomag line for age, and it's asymmetric in the East Pacific Rise. And he looked, the colors here are telling you the residence time, where in the hotspot reference frame the East Pacific Rise has been in the past. And relative to other ridges, it's actually been pretty stationary, so always in the same location. So maybe that part of the spreading center, it's a different kind of view of plate tectonics, not being controlled just by subduction, but this upwelling underneath the East Pacific Rise being kind of important. So anyway, that's just one little thing that you can find from these kinds of models. So I had wanted to talk about the boundary conditions and doing all of this work. I'm a seismologist, not as a geodynamicist. I'll leave that for the question period if anybody's interested in that, because I kind of discovered in the last year kind of an important issue. So I'll jump right to the conclusions. I think joint inversion is a good approach to looking at the dynamics of the mantle, no matter how you're doing your tomography or how you're doing the geodynamics. I kind of like this. Turns out the surface boundary conditions are important in geodynamics, and we can talk about that after if there's any time. And then I had a few other conclusions here for the particular results we showed in this talk. So I'll finish there. And
okay. Thank you, Stefan.